Hi, I'm Sala. In this third video of the case study on this simple second-order process, we'll address scaled small gain and H-infinity synthesis. In previous videos, we just had a PID and we analyzed the meaning of robust performance, both in a simulation-based framework or in a generalized planned theoretical one. So we will review those results and try to replace the hand-tuned PID with an optimal H-infinity controller. We had this model and this additive uncertainty bound of 0.2. We had this hand-tuned PID for which we thought nominal response to a reference step was a reasonable one. We also thought reasonable the frequency response from set point to error, and we simulated random plants within the ball of uncertainty, and we decided that from a simulation point of view, this was reasonable. Our problem was to certify that this was not just a matter of good luck, so we wished to certify that there does not exist any other plant in the ball of uncertainty whose response would be rubbish. So we first proved robust stability with this code. We saw that our uncertainty was below the robust stability bound by a factor of 2.5, and also we proved not only that the loop was going to be stable, finite, not bound, but also we sought proving that in the face of modeling errors, the set point to error closed loop frequency response will be below the red bound. In order to do that, we propose this generalized plant and the weighted generalized plant encircled in cyan color. Actually, we proposed S equal to 1, so we had an uncertainty weight of 0.2 that multiplied a standardized norm 1 uncertainty, and then a reference amplitude of 1 and the inverse of the error template in here. So with that weighted generalized plant, we could use this result, which says that if the norm of the generalized plant P without uncertainty, because it's unknown, if the norm of P is lower than 1, then we achieved our robust performance goal. So even without a multiplier, as this thing was below 1, we proved our robust performance. However, we realized that if we had put the bound of delta at the input side, this would be 2.11, even if the problem, in theory, would have been equivalent. I mean, our new version of the code would have been this. But, as we hinted, we have a sort of hidden degree of freedom with a multiplier S, because our uncertainty of 0.2 can be conceived as, let's say, a gain of 20 uncertainty of norm 1 and a gain of 0.01. That gives also an equivalent representation of that uncertainty. The generalization of that is called scaled small gain theorem, so we can look for a multiplier S in order for our weighted generalized plant to have norm less than 1, as this theoretical result requires. So we have a degree of freedom on the multiplier S, and even if here our controller K was fixed, it was a PD, in fact, we can minimize the H-infinity norm of this system in closed loop with H-infinity synthesis to try to improve performance with respect to the PID. So let us see how it fares in MATLAB. We will now replace code with the scaled small gain stuff. I moved the bound of delta because, in my previous video with that thing S equal 1 did the job. But, 1.2 has a smaller norm, not 1.3. 1.1 is also slightly worse. So with an S close to 1.2, we can sort of push a little bit more. So we might be able to increase the performance level we are trying. But nevertheless, we can now, instead of doing the PID, just computing the H-infinity controller that minimizes the closed loop norm. Of course, my PID gave 0.96 roughly, and my optimal H-infinity controller gives, of course, a better figure for the norm value, 0.87. So this means that, for instance, with this controller, we can increase our performance requirements, or we can increase our robustness requirements, proving the same performance for a larger modeling error. So, for instance, let me first try a more robust design, just looking for an additive bound of 0.4. Then, if I execute everything with this doubled additive error size, the open loop step response is wider, and my PID performance suffers from high uncertainty in the first stages, as well as this undesired peak in high frequency components of the error. Indeed, our sensible bound for robust performance is violated, so with the PID, this is greater than 1, and given that we have seen a counterexample, a violation of our bound, we cannot be able to find a multiplier that makes this number below 1. You can try as much as you want, but the theory says that we will not be successful. However, with our H-infinity controller, let me comment this, the multiplier of 0.6 is not good, but 0.9 is almost there. 1.2 proves it. But, okay, by trial and error, let's say I found that 1.8 gets me almost a 10% extra margin. So given that we have extra margin, we can try to find a controller for a even larger uncertainty bound, or well, now if we are happy with our current uncertainty bound, we may pursue faster performance. So instead of target bandwidth of 0.85, I may move my performance requirements towards the higher frequency ranges, and faster set points would be followed with lower errors. If I change to 1.25, my nominal PID still meets that criterion, but of course the modeling error will make this to result in some random plants quite above our limit. But well, our H-infinity controller is almost there with 1.8 multiplier, but we don't seem to be able to get below 1, so we pushed a little too far away the robust performance requirement maybe. But if I change it to 1.1, the multiplier 1.6, it's almost there. Well, it seems that I cannot yet reach below 1, so I need to put a bandwidth of 1.05. Let's see. Okay, now playing a bit with the multiplier, I got this with this value of S, it's kind of trying, okay? Our goal would be, of course, either maximizing the tolerated uncertainty bound or the performance level, bandwidth, let's say, or a mixture of both of them, as we did here. If we simulate time response and frequency response of the latest H-infinity controller, this is what we find. Again, this kind of behavior in the initial phases is the picture in the time domain of this kind of strange things in the frequency domain, but okay, it's below our red line. If we are not happy with that, then maybe we should have, instead of increased the bandwidth as we did, we might have lowered this high frequency gain to lower these peaks, guiding the H-infinity controller in a different direction. So this is it. Let us conclude. I give a couple of important remarks. In this video, we explored scaled small gain with a multiplier here in this particular setting, whose general setup in abstract sense is this kind of block diagram with a generalized plant. So with an H-infinity controller synthesis and the search of the multiplier, we were able to improve with respect to an initial PID. No surprise, because okay, it was just a hand-tuned PID, so it was not bad, but our controller now was a little bit faster and tolerated double uncertainty, at the expense, of course, of an additional complexity of the resulting controller and the design procedure. Our H-infinity controller cancelled the plant because there were no input disturbances, so our optimizer does not look for a good input disturbance response. These cancellation controllers may give problems with slow input disturbance response, and this is common to, let's say, mixed sensitivity or internal model control designs, but okay, if they are not in the generalized plant, the optimizer cannot optimize for them. So if we are not happy with input disturbance response, then we should include them in the generalized plant. This is remark 1. Remark 2, we looked for the multiplier just by, trial and error, manually testing some numbers. Okay, this is kind of a shame. How do I dare doing that? This video is supposed to be the first approach to this robust performance problem, and then I wish to keep it simple. But of course, we could at least have thought in, trying the multipliers in a loop, testing 100 of them, without manually testing each of them. Or we could have used the optimization toolbox to find the multiplier that minimizes this. Or, well, what mu synthesis exploits is the fact that for a fixed controller, finding the multiplier that minimizes the norm of this block diagram is a convex problem. So, mu synthesis kind of tries to do it in the better known way. It's not convex overall. It can get stuck in local minima, but okay, the algorithms they implement are far better than the manual search I was doing this. So I am not claiming that this is the way to solve this problem, okay? This is just a first introduction to what robust performance and scaled small gain means. So we finish it here. Thanks for watching.